It is our pleasure to have as the last event for YMC 2021, the plenary talk by Dr. Jose Perea. He will speak about topology in computer vision. Dr. Perea is an associate professor in the Department of Mathematics and in the College of Computer Sciences at Northeastern University. He received his PhD at Stanford University. He was advised by Gunnar Carlson, and his research is in topological data analysis. He received numerous awards. For example, he's a career award recipient. This is the NSF most prestigious grant award for early career faculty. He was also mathematically gifted and Black 2018 honoree. There is a very nice article interview with him. I'm going to post a link in the comments. But from that article, I would just like to quote his words for young people. He said, and it's written there, luck is when preparation meets opportunity. So put in the work. Even the people that you perceive as being super successful deal with insecurities and feeling of inadequacy. So I'm going to post the link in chat. So Dr. Perea will talk about topology in computer vision.
Thank you, Radhika. That was a very generous introduction. And thank you all for being here. I hope that the event has been enjoyable and that hopefully you've learned a lot and you're carrying with you sort of cool memories and experiences. So topology in computer vision. So let's see how this goes. So when scientists are trying to understand a certain phenomenon, they typically go out in the wild and they collect data. This happens in biology, computer science, and physics, but it also happens in mathematics. So let me show you an example of how that works in real life. So here is hopefully a video. And then, let's see, so Zoom is being, okay, here we go. So here is a video now. Okay, great. So I'm gonna do it slowly again. So what she's doing is she's releasing a tennis ball, and then what they're doing is they're tracking the motion of the ball as it moves through the air. And the black line is just a result of sort of plotting the path of the ball. If you wanted to understand the motion of the ball, then of course, as I said, you could collect data. And by data, I really mean perhaps the time steps. And then at each time, you measure the position in the horizontal axis, that is the x coordinate, and you record the position in the y-axis, that's the y coordinate. So your data is sort of composed of time steps, positions in the horizontal axis, and positions in the vertical axis. And let's say that the goal is to understand, again, the movement of the ball. So if you have the data, and we do, then the thing that you could try to sort of figure out is, by plotting it, is first of all, what is the shape of the data? And this is going to be a question that we're going to come back to many times over the talk. What is the shape of the data? In this case, it is very easy because we can plot it, we can see it. For example, here I'm plotting the x coordinate versus time in the left panel, and then the y coordinate versus the x coordinate in the right panel. And so the first thing we see is that the shape of x versus t is linear, and the shape of y versus x is parabolic. And unfortunately, we have sort of the math toolbox to express those relations in terms of equations and formulas. So the fact that x depends on time in a linear fashion can be recorded saying that x is equal to m plus t, m times t, and that y being parabolic in x can be expressed as this sort of degree 2 polynomial, where m, a, b, and c are all real numbers, which using the sort of magic of calculus, we can sort of approximate very well, right? So we can take the data and we can find the best M, A, B, and C that will fit our data the best, okay? So once you do that, you are sort of in this godlike situation, right? Where you have entire control over the system. If you tell me what is the position in X, I can use my formulas without having to watch the video and immediately tell you what the position is going to be in Y. If you tell me the time, I will be able to tell you both X and Y, right? So that's sort of godlike complete control over the system because you were able to, one, figure out what the shape of the data was by looking at it, and two, by finding appropriate mathematical expressions to capture that, okay? So what I'm gonna do now is I'm gonna switch the data set, but I'm gonna ask the same question, okay? So the data set now comes from this very interesting library, the COIL 20 database. This is the Columbia University Image Library. It is composed of 20 objects. And then for each one of those objects, you take 72 photos in different poses of the object. So for example, one of the objects is this rubber duck. And you have something like 1,400 images. And what do I mean by images as data? So if you look at a photo, even though it may look as a sort of a smooth thing, actually, when you look at it very, very close, you will see that it's made up of pixels, and those pixels can be represented via numbers. For example, the 7x7 pixel is actually produced by inputting the numbers that you see on the right. So if you have an n by m image, as the one on the left, then we can just think of it as an n by n matrix. And what we're gonna do always is we're gonna take the columns of that matrix and we're gonna concatenate them into a giant vector, right? So it's gonna be a long list of numbers of size n times m. That is okay. It's just gonna be a point in this high dimensional Euclidean space, okay? In the example of the ball, we only had 3 components, so it was very easy to see the data. When you look at data comprised of images, the power to see sort of goes away a little bit, and you have to be a little bit more sneaky. So the data that we're going to look at is going to be the collection of all the poses of the rubber duck. So that's the data. As I said before, I'm going to take each one of those images. I'm going to turn it into a long vector. That's just a point in some giant Euclidean space. And by looking at all those points, I want to ask you, the audience, what is the shape of the data? So does anyone have a guess? Feel free to unmute yourself and tell us. I'll take a sip of coffee in the meantime. Okay. Jason, are you, yeah.
Can you think about it as being roughly spherical or 2 spheres? So,
oh, interesting. Those are,
yeah.
Yeah. Sorry, can you say more? Why a circle or why a sphere?
It's connected, right? So it is, yeah, it's connected, and it is roughly spherical. Or, I mean, if you sort of continuously deform it, it is a sphere.
Interesting.
So if we look at it in terms of homology groups, then at least 0th homology group 1 and 1st homology group 1. Yeah,
those are all the right words. We'll see if they are spoken in the right order. But so here's what we're gonna do. We're gonna do a demo. So hopefully you're seeing a MATLAB interface right now. Is that true? Okay, great. So I'm gonna run some code that I wrote, and then what the code is gonna do is we're gonna visualize the data, right? So we're gonna take all of those images. As I said, each one of them is gonna represent a point in a giant Euclidean space, and then I'm gonna do some machine learning trickery to visualize the data set. So let me go ahead and run it. Hopefully it'll work. It works. It's just that you guys are not seeing it yet. Now let me move it. Okay, here we go. So this is the data. So as Jason suspected, the shape of the data is roughly circular. So hopefully you're seeing a bunch of points, a bunch of dots, and those dots trace a circle. Just to remind you again, each dot is an image. I just took it from this giant Euclidean space and somehow represented it in this lower Euclidean space so that we could see it. If you want to explain as to why the data is circular, you have to do a little bit more work. And I'm going to do that next. So, so hopefully, I was hoping the images will just come out in the right place. But so here's what I did. So I placed the images of the dock in each one of the coordinates I computed. And hopefully what you can see is that going around the circle is essentially turning the dock around. So again, we are in this godlike situation where we took the data, we figured out the shape. It's not a line, it's not an ellipse. Those formulas are not going to work, but it's a circle, and we know circles, those are nice. And we know that by plotting the data along the circle, we can essentially figure out what the circle is parameterizing. It's parameterizing the orientation of the dock. Okay, so this is what topological data analysis is all about, is taking data, is asking what is the topology of the space that underlies the data. In some cases you can see it, in some cases you can't, so you have to be more creative. But then you have to explain why that shape arises, okay? I'm gonna go back to the PowerPoint presentation, but before I do that, are there any questions? Okay, so we'll go back to PowerPoint. What is topology? So in topology, we think of objects as being equal up to continuous deformations. So we think that everything is made out of Play-Doh, and that you can take a triangle, you can deform it into a disk, and you can deform it into a square. And the reason why we think of it that way is because if you remember the docks, the circle wasn't like a perfect round circle, but rather it was like a squiggly circle. But still, that was enough for us to make inference, right? So we're going to think of objects up to continuous deformations. The joke that everybody makes is that topologists cannot tell apart a donut from a coffee mug, because you can deform one into the other. And hopefully you can see the animation in the middle, deforming the donut into the coffee mug. So that's what topology does. Topology tries to understand objects up to continuous deformations. And we try to compute things about them, right? So how do we compute things about spaces? So the first thing we do is we take these spaces and we simplify them a little bit. For example, here's the circle. And what we do is we triangulate it. We divide it into pieces that are simpler. So for example, here, I divided it into sort of 3 segments and 3 vertices. And I have 3 vertices, 3 edges, and sort of 0 triangular faces, if you will. So this is a triangulation of the circle. You may find the word triangulation confusing because you're not seeing any triangles or any straight edges. But again, I tell you that in topology, we don't care about things not being straight. So this edge really is an edge. This vertex really is a vertex, and so on. The torus is another space that we like very much in topology. It is the surface of the donut, and you can think of it as a circle Cartesian product with itself. A model that I like for the torus is, take the square, and what you're going to do is you're going to take the top edge and you're going to paste it to the bottom edge. That would give you a cylinder. And then you take the left edge and you're going to paste it to the right edge in the same direction. And when you do that, you recover the torus that you see on the left. The square model is nice because it is easy to triangulate. So for example, here I've divided the torus into edges, vertices, and then triangular faces. For example, here I have 9 edges. I believe that I have 18 triangular faces. And again, the reason why we triangulate spaces is because we can then compute things about them. And by compute, I really mean with computers. Here's the Klein Bottle. This is a very nice, very interesting space. The way you get the Klein Bottle is similar to the Taurus. You start with a square, you take the top edge, you paste it to the bottom edge. Again, you get the cylinder. But then what you do is you paste the left edge opposite to the right edge. So instead of coming sort of straight like when you were constructing the Taurus, you have to sort of go into another dimension and come back from the other side to paste it in the reverse direction. So when you do that, is that you get the Klein Bottle. And again, you can triangulate it, and we can compute things about the Klein Bottle that way. The last space I'm going to describe is sort of very close and dear to my heart, is the projective plane. One way to think about it is as the collection of linear subspaces of R3. So vector spaces inside of R3 that have dimension 1, just lines passing through the origin. Another way to think about it is as follows. This is another model that I like. Think of a disk, and then what we're going to do is we're going to identify points in the boundary if they are diametrically opposed. So the A that you see on the left is the same A as you see on the right. And the idea is that if you are sort of walking, on the projective plane and you get to this A, then you get sort of teleported to the other A. So that's the sort of other model for RP2 that I like very much. Here's a triangulation of RP2. And again, we can use that triangulation to compute things about RP2. So thus far, I've given you 4 examples of spaces. I've given you triangulations of them, and I've promised that we can compute things about those spaces. One of the things we can compute about triangulated spaces is their homology. So this is something that Jason mentioned at the beginning. So we're going to compute the homology of what are called simplicial complexes. So a simplicial complex is a space that is very simple, that is built out of very simple pieces, in particular triangles, edges, and vertices, right? So here in the top right, I'm showing you one of those simplicial complexes. It's a space that is, as I said before, built by gluing together simple pieces, vertices, edges, triangles, and so on. The thing in the bottom right is not a simplicial complex because the simple pieces are not sort of glued in a nice way, okay? So they sort of intersect in weird ways. What we're gonna require, though, is that for something to be a simplicial complex, the triangles, the edges, and the vertices can only meet at their boundaries, can only be glued at their boundaries, okay? So that is a simplicial complex, space that is made up of simple pieces glued in a very nice way. So what is the homology of a simplicial complex? So the first thing we're going to do is we're going to fix a field that can be the rationals, the real numbers, the complex numbers, or the integers modulo a prime. The last example is particularly useful in sort of when you're doing things in computers. The next thing what we're going to do is we're going to fix a non-negative integer in a simplicial complex K. And then I'm just going to say some words, and hopefully they'll make sense to you. So the symbol HN K, F is what we call the nth homology of K with coefficients in F. The nth homology of K with coefficients in F. I haven't said anything yet, right? But what is it? It is a vector space over F. And what is important is the dimension of that vector space captures the number of holes in the space in dimension n. I'm gonna dedicate the next 10 minutes or so to explaining that comment. But for now, the nth homology of a simplicial complex with coefficients in a field F is a vector space, and the dimension of that vector space indicates the number of holes. So let me give you a little bit more context. So let's take this simplicial complex K, right? Very simple. If you compute the zeroth homology, let's say with coefficients in the real numbers in R, then you get a real vector space, right? So you get something that is some number of copies of the real numbers. In this case, you get R3, 3 copies of the real numbers. So why do you get that? Well, zero, the sort of the zero-dimensional holes, is nothing more than the number of connected components that the space has. So again, 0 measures number of connected components in your space. If you look at the simplicial complex we have this vertex all by itself, we have this other piece that is connected, and we have this other giant piece that is also connected. So 3 connected pieces. That's why when you compute the 0 homology, you get R3. The dimension is 3 because you have 3 connected components, okay? So again, remember, 0 equals connected components. When you compute the first homology of the space, you're computing sort of number of one-dimensional holes, okay? So again, if you go to the complex and you see this lower right sort of triangle here, you will notice that it's not filled in. And that is the only sort of circular hole that you're seeing in the space. That's why H1 of K is just R, just one hole, vector space of dimension 1. Okay. Let me show you more examples, and hopefully we'll start to build intuition as to how this works. So again, here's the circle, triangulated and all. And as I said before, if you compute homology dimension 0, with coefficients, this time we're doing in Zima 2. So you should get only 1 copy of the field, right? Because you have only 1 connected component. In dimension 1, you get 1 copy of the field because again, you have this circle, which is a one-dimensional hole. And if you look in higher dimensions, you get nothing because the circle doesn't have holes in higher dimensions, okay? So hopefully that was sort of confusing enough to pique your interest, but clear enough to give you some intuition, and we'll see if that paid off. So here's the torus again. In dimension 0, you get 1 copy of the field because again, it's connected. So let's do a poll. So in the chat, could you type in, excuse me, could you type in the chat what you think the answer is gonna be for H1? In other words, do we have 0 holes, 1 hole, 2 holes in dimension 1? And then I'll see in the chat what we get. I like the question mark. Okay, so there's a bunch of 2s. There are no 1s. Interesting. Okay. Okay. So thank you for your participation. You were all very correct. There is a horizontal hole in blue. There's a vertical hole in red. And that means that when you compute H1 of the torus, you get 2 copies of the field. 1 copy for the horizontal hole, another copy for the vertical hole. Now, when you compute H2, again, here you're asking about 2-dimensional holes. In other words, sort of closed surfaces that bound empty space. It turns out that the torus itself is a 2-dimensional surface, and it bounds a 3-dimensional empty space in the middle. Therefore, H2 of the torus is just 1 copy of the field. And then in higher dimensions, you get 0. Okay, excellent. The projective space is nice because it's sort of the first example where changing the field of coefficients gives you something different. So again, RP2 is connected, 1 copy of the field in dimension 0. In H1, you get 1 hole in Zima 2. The way I like to think about it is that if you go from the vertex 1 to 3 to 2 to 1, that is a closed loop in RP2. Again, I'm going from 1 to 3 to 2 to 1 again. It's a closed loop. And what you have to somehow convince yourself is that that loop doesn't bound anything. It's an honest to God hole inside of RP2. It turns out that that hole disappears if you change the field of coefficients to Z3. So if you change the algebra, the whole suddenly goes away. Let me explain why that happens. Again, I'm gonna go from 1 to 3 to 2 to 1. And again, from 1 to 3 to 2 to 1. So what have I done? I've traversed the whole 2 times. Again, 1 to 3 to 2 to 1, and again, 1 to 3 to 2 to 1. Going around the whole 2 times is filled in by all of RP2. So all of RP2 is sort of this 2-dimensional thing that is filling up that sort of going twice around the whole. Here's where the algebra makes a difference. If you look at Zima 2 is equal to 0, so that doesn't tell us much. But in Zima 3, 2 is equal to -1. So he's saying that going around the hole in the opposite direction is filled in. So that's why it's 0 in Zima 3. If this doesn't make sense to you, don't worry. It doesn't make sense to many grad students that I've met. But the gist of it is that there are some spaces that are complicated enough that if you change the field of coefficient for your homology, the answer is going to change. And then sort of this intuition of holes sort of breaks down because of that. But nonetheless, homology is still useful to compute properties of shapes for spaces. And then for my last example, I'll just run very quickly through this. The Klein Bottle, homology with Zima 2 and Zima 3 coefficients. If you look at it with Zima 2 coefficients, it looks like the Taurus. But if you look at it with Zima 3 coefficients, it looks like something very different. So the Klein Bottle is complicated. Who knew? So homology is a great invariant. Here's a theorem for you guys. Homology is invariant under triangulations and continuous deformations. So what does that mean? It means that if you take your space and you triangulate it differently, the answer you get when you compute homology is not going to change. And the other thing that happens is that if you deform your space a little bit continuously, the homology is also not going to change. So it's the kind of things that topologies like very much, because the homology of a space can be used to tell spaces apart, which are not a deformation of each other. So these ideas around homology, we owe them to people like Enrico Betti, Henry Poincaré, and namely Emmy Noether. So before Emmy Noether, homology was treated as essentially numbers, so the Betti numbers. But it was Emmy Noether who said, no, we should really treat them as groups and rings and vector spaces. So that's huge, and we'll see in a moment why. So again, 4 spaces: Klein Bottle, circle, projective plane. We computed their homology. For example, with Zima 2 coefficients and dimension 1, we get the following sort of count for the number of holes. So right away, we know that the circle and the torus are different, right? They have different homology in dimension 1. And the circle and the Klein Bottle are different. They have different homology in dimension 1. But there is sort of ambiguity between the torus and the Klein Bottle and the circle and the projective plane. So if you change the field of coefficients, notice what happens. So now we disambiguate the circle and the projective plane, and we disambiguate the torus and the Klein Bottle. So all of these spaces are different, are honest to God different. Their homology is different. We cannot deform one into another continuously. So if a friend of yours now asks you, how do you show that it's not possible to deform a Klein Bottle into a Taurus? Now you can say, their homology is different, and that's enough. So going back to data, and again, the talk started with the question of the shape of data. How do we measure shape? So now here's a data set. Hopefully it reminds you of the docs. And you can ask, what is the shape? It's a circle. But it's really not, because it's just a collection of disconnected points. There is no way that you can sort of trace a closed loop continuously around the data. But here's something we can do. We do sort of the obvious thing, right? So we start sort of drawing edges and triangles and tetrahedra for points that are very close to each other, right? And then we increase the tolerance of what we deem to be close. And hopefully what you're seeing is that at each stage, we're constructing a simplicial complex that hopefully reflects the fact that there is a circle underneath, or at least topologically, that's what we think should happen. So I think now the animation is going to start again. And again, the thing to remember is that we're constructing these simplicial complexes at different scales, you know, and we say we're going to join the points that are very close together with an edge. If 3 edges have been drawn, we fill in the triangle. If, you know, 6 edges have been drawn, we fill in the tetrahedron, and so on. And we do that for increasing scales. And the goal is to analyze how the topology, and in particular the homology of these simplicial complexes changes across scales, okay? So persistence. So in persistent homology, what we do is instead of looking at each simplicial complex separately and try to figure out what is the best epsilon or what is the best scale to join points, instead of doing that, what we're going to do is we're going to look at all scales at the same time. Okay, so we're going to look at all the simplicial complexes we get by considering, you know, joining vertices that are close. We can compute their homology, right? Now we get vector spaces at all these scales. And if you have taken linear algebra, hopefully you have, you know that if you have a vector space and you believe in the axiom of choice, you can pick a basis for each one of those vector spaces. And then not only do we have simplicial complexes, but we know that we have sort of this increasing sequence of simplicial complexes, right? Like one is containing the other and that is contained in the next. So we get actually linear transformations between the vector spaces that you get from homology. And again, if you have taken linear algebra, and I hope you have, then you know that linear transformations are nothing but matrices. And if you like matrices, hopefully you know Gaussian elimination. And you know that you can change the basis to something much, much more nice, right? Like you go from the purple basis where the matrix is weird to the blue basis where the matrix is very, very simple. And what the matrix is telling you is that the first basis element is being taken to the first basis element, that the second basis element is being taken to the second basis element, and that the third basis element is being taken to 0. And all of that can be encoded with arrows and dots. The magic of the linear algebra tells you that you can do that for all scales at the same time. So we've chosen bases for all these vector spaces, and we are able to track how the homology changes from one scale to the next. This is the most important slide of the talk. It's the idea that using essentially linear algebra or you know, abstract algebra, we can track how the holes in the data sort of appear and disappear, how they are created when they appear here as a basis element, how they persist, you know, when the arrow continues, and then how they die or how they're filled in when the linear transformation sends them to 0. Okay, so going back to the docs, a circular data set, I went ahead and did the procedure that I described. I looked at the data at all scales. I computed the homology in dimensions 0 and 1, and I tried to see how the homology changed across scales. And here's what I got. The horizontal blue lines, think of them as the arrows I showed you 2 slides ago. So what you're seeing, hopefully, is that in dimension 0, you start with a bunch of basis elements, which at some point become 0. And only one of those basis elements persists for a long, long, long time. If you remember what we talked about in homology, you will recall that dimension 0 is all about connected components, right? So it's telling you that there is one connected component that persists in the data. So that tells you the data is connected. The data is connected. Now, if you look at dimension 1, you will see that there is this long bar. Again, you think of it as a basis element that persists for a very, very long scale. So that is telling you that the data has a hole in dimension 1 that is very persistent. And that is sort of consistent with the dots lying around the circle. So the circle is the one-dimensional hole that persists throughout. So this is how we can capture the shape of data using homology in computers. The sort of final example I'm going to sort of show you before we jump into computer vision is the Taurus, our old friend, the Taurus. So again, I've recorded the homology here at the top right, just for you to remember it. And then what I did is I sampled the Taurus. I took a bunch of points, which you can see on the lower left. And then I did the same procedure I described. Someone is, okay. And then I guess what I was saying is that hopefully you can see the bars in the bottom right in dimension 0, 1, and 2. Again, dimension 0, connected components, dimension 1, cycles in one dimension, dimension 2, surfaces which are closed and bound a void. And again, hopefully the number of long bars coincides with the dimension of the homology vector spaces. So this is it. That is how people in topological data analysis measure the shape of data. We compute barcodes as a surrogate for the homology, and we use the barcodes to tell us what is the shape that we're looking at. Let me pause here for a minute. There must be questions. So any questions? Feel free to unmute yourself if you want to.
Are there any fractal geometry aspects in those barcodes?
Oh, that's a great question. So let me see who asked it.
Dane.
Dane, great, Dane. Yes, yes. So fractals are spaces which are self-similar as you vary the scale, and that is actually very nicely recorded into these barcodes. So there is not recent, but there is work by Robert McPherson and one of his collaborators where he shows how one can use sort of these barcodes to measure fractal properties of spaces. So things like the Sierpinski triangle or self-avoiding random walks. And again, especially dimension 0 is related to things like the Hausdorff dimension of a space. And one can make all of that precise. Yeah. Thank you, Dane.
Cool, thank you.
Yeah. Okay, so so how are we doing with time? Okay, we have like 20 minutes, okay. Or 10, I don't know. Radhika, how much time do we have?
20 minutes, yes.
20 minutes, okay, thank you. Okay, so for the perhaps more algebraically minded, let me tell you what is happening in the background. And this is actually how the algorithms came to be. So if you have a sequence of spaces which are included into each other, then the homology again gives you vector spaces and linear transformations between them. One can compute something called the persistent homology, which is just the direct sum of all of those vector spaces. And one can show that the persistent homology is in fact a module over the polynomial ring in one variable, ft. And then what one can show more than that is that there is something similar to the classification of, let's say, finally generated abelian groups. So if you guys have taken algebra before, you know that if you have an abelian group and it's finally generated, then it's isomorphic to a number of copies of Z plus a number of copies of Z mod N. And something similar happens here. One can show that the persistent homology is a number of copies of something that looks like the ring, and a number of copies of things that look like the ring mod something. And it turns out that from that decomposition, one can read off the barcodes. The barcodes are sort of the free part of the module. The infinite bars are the free part, and the finite bars are sort of the torsion part of the module. And when you do that, and you get sort of these intervals, that is exactly what we're computing here in the bottom right. We're computing the invariant decomposition of some module that is interesting. If you want to know more about the algebra, I would recommend the paper that sort of introduced the idea. So let me now jump into computer vision, which is where we try to teach computers how to see. Neural networks are very powerful and very popular these days. They're used for things from self-driving cars to the things that are on your phone, like speech recognition and image recognition. A particularly useful kind of network is what is called an autoencoder. So an autoencoder is a network where you try to learn the identity map, meaning that the input network has the same dimension as your data, the output network has the same dimension as your data, and there's like a funnel, there's like a bottleneck where you have very few neurons. And again, the reason why you try to learn the identity map is because then the neurons in the middle act as encoders for the data. And again, these are used in things like self-driving cars. So if you take one of these autoencoders and you train it on natural images, the sort of photos that we see every day, what scientists have shown is that the neurons that are trained through this process tend to be edge detectors. What do I mean by that? Here in the right-hand side, I'm showing you images such that each one of them is the image that most excites one of these middle neurons in an autoencoder trained on natural images. In other words, you can think of this as the neurons that the network learned to look for in an image. Okay, so a simple data science question is, what is the shape of that data? What is the shape of the collection of edge detectors, of neuron detectors, of edge detector neurons that we've learned? So I'm going to give you a homework if you're getting bored, and we're going to come back to it at the end of the talk. So here's the data set. The data set is comprised of images of a single straight line. The line has fixed thickness, but we're going to allow the line to rotate and to be translated, okay, even outside of the image. Fixed thickness, variable orientation, variable translate. 7 by 7 images. We're going to think of them as before as a subset of R9. Question, what is the shape of that data? What is the shape of the collection of points that you get in this fashion? I've gone ahead and computed the persistent homology for you. In dimension 0, and with Zima2 coefficients, you see sort of a long bar, meaning that it's connected. In dimension 1, you get 1 bar, meaning that there is a one-dimensional hole. In dimension 2, you get 1 bar that is a little bit longer, meaning that there is a two-dimensional hole in the data. There are many spaces that have that homology, right? You can think of, for example, like a sphere with a circle attached to it that would have the same homology. If you change the field of coefficients to Zima3, it turns out that the one-dimensional feature now goes away, and the two-dimensional feature now goes away as well. So hopefully with that information and the spaces we've seen, hopefully you can hypothesize what the shape of the data is. So again, if you wanna take a Zoom break and try to think about this, we're gonna come back to it at the end of the talk. What is the shape of the data? So that's what machines, someone asked a question. Jason, did you just ask that and I missed it?
It was while you were explaining the abstract algebra part. I can ask it at the end. Thank you.
Okay. Yeah. Okay. So this is what machines see. The question now is what do humans see? So the following experiment was carried out in 1999. It's a great experiment. It's trying to figure out what do humans pay attention to when they look at images? So what they did is they took, participants, show them natural images, photos, and sort of tracked where their eyes were sort of concentrating on. So the path that you're seeing here is sort of the path that the gaze of one of the subjects followed. So that experiment sort of generated the following sort of research line. The idea of, let's take a bunch of images. In particular, there's this data set, the J. Van Hateren natural image data set. It's got something like 4,000 images just taken outside, and then trying to ask questions about, what are the most important areas within these images that humans pay attention to. David Mumford and his collaborators in the 2000s did the following experiment. So they took 3x3 patches that have high contrast from this collection of natural images that I just showed you, right? So 4,000 images, from each one of them, you take 3x3 patches that have very high contrast, and we're gonna treat them all as points in R9, okay? So that's the initial data set, 3x3 high contrast patches from natural images. That is suggested by the sort of earlier work where you see that humans pay attention to high contrast areas within images. So they did the following two operations to this data set. They deemed two of those patches to be similar if they differed by a constant, right? So they sort of center by intensity, and then said, we're gonna take two of those patches to be similar if we can normalize by contrast and we get the same thing, right? So we're doing two transformations. We're centering via a constant, an additive constant, and we are normalizing via a multiplicative factor. So these are the kinds of images that you get from that process. You get sort of these 3x3 patches that have high contrast and very sort of interesting geometries. And again, the question is, what is the shape of that data? So a little bit of thinking sort of reveals that by starting with something in R9 and then doing these two simple linear transformations puts the data inside of R9, right? Sorry, inside of a 7 sphere in R9, okay? The additive constant removes one dimension, and then the normalization constant puts you on the sphere. Two things are true about this data set. It fills out the entire 7 sphere, but then not all of the areas are equally densely populated. So what one tries to figure out is, what are the areas that are most important in this 7-dimensional sphere? Sorry, give me one moment. There's something making a weird noise here in my house. When you do Zoom. Okay, we're back. So here's what we're gonna do. We're gonna try to understand the areas with high density from the Mumford data, right? Sort of these 3x3 patches that have high contrast from natural images.
Sorry, we do see your presentation view on the slides. I'm not sure if you wanted to show us that one.
Oh, the presentation view.
Yes.
How about now?
Yeah, looks good now.
Okay, great. Thank you. Apparently, I'm out of practice with Zoom. Okay, let's start again. Mumford data, 3x3 patches from natural images with high contrast. We put them on the 7 sphere. We realize that they fill out the entire 7 sphere, but not all pieces are equally densely populated. So we're trying to look at the areas with highest density. Okay, so here's how we do it. For each point in the data, we measure its distance to its nearest neighbor, to its kth nearest neighbor, right? For some k, and this is a parameter of the process that one has to figure out. The thing to notice is that if you take 1 over delta k, again the distance to kth nearest neighbor, this acts as a measure of density. right? And then we can look at sort of the top densest points inside of the data measured through distance to their nearest neighbors, okay? So if something is very dense, all of its neighbors are very close, and then this rho K is gonna be very large, okay? So here's the answer that sort of Carlson and others got when they looked at this data. Homology in dimension 0 or persistent homology in dimension 0 gives you something connected. In dimension 1, you get 2 holes, at least with Zima2 coefficients. So you go back to your sort of database of spaces that you know from taking topology. And you compute homology in dimension 1, and you remember, oh, the circle only has, 1 hole, RP2 only has 1 hole. It cannot be one of them. So you delete them from the list. So it can only be something like the Taurus perhaps, or something like the Klein Bottle. Okay. The thing to notice now is that if you change the field from Z2 to Z3, the Taurus still has 2 generators in dimension 1, but the Klein Bottle loses one of those generators when you switch fields. So we go to the data, and we compute persistent homology now with Zima3 coefficients, and we see that again one of the generators in dimension 1 is lost, right? So that right there tells you that the data is probably accumulating around the Klein Bottle. So that's the shape of the data that one hypothesizes. And in fact, you can actually come up with a model that shows you how sort of the most important 3x3 patches from images can be placed to parameterize a Klein Bottle. So let me walk you through it. The 2 types of patches that turn out to be the most important ones are things that look like linear gradients. So things that go from dark to gray to white, and then quadratic gradients, which are things that go from dark to light and then to dark again. The horizontal direction in the Klein Bottle is parameterizing sort of the orientation of the patch, right? So you can see that when you go from left to right, what you're doing is you're rotating the gradient of the intensity. And hopefully what you can see when you go from bottom to top is that you are interpolating between sort of quadratic gradients to linear gradients, quadratic gradients again, linear gradients, and then quadratic, but darker at the end, right? And by going through the edges, hopefully you can see that this is an honest to God Klein Bottle. So this is it. This is the kind of process that we do in TDA, which is you have a weird data set that you don't understand, but that is interesting for some reason. You wonder what the shape of it is. So you compute something like persistent homology. The barcode suggests spaces that perhaps are useful. And then you use other means to figure out interesting models for your space, right? So hopefully this is not a parabola. It's not a circle, but it's still an interesting parameterization of something that we care about. And in the last few minutes of the talk, I'll tell you why these models are useful. So the conclusion that we have now is that most small patches from natural images, at least the high contrast ones, accumulate around a Klein Bottle with high density. That's the whole conclusion from this adventure. And here's something that we did with that model. We taught the computers how to tell texture images apart. So here are 2 images of textures, brick and hay. If you look at just one of these images, so let's say hay, and you take its small 3x3 patches, like we said before, they accumulate around this Klein Bottle. And then different images are going to give you sort of different points around the Klein Bottle, right? So here's what we plan to do. We're going to take our image, we're going to take its patches, and we're going to project them onto the Klein Bottle. Okay. So here's what I did. I took a 3x3 patch from the image of bricks, and I looked for its closest point on the Klein bottle. And I did that for all the patches in the image. The heat map that you're seeing on the left is the pieces where we found sort of most patches from the image. And the areas in blue is the areas where we find less patches from the image. So hopefully by looking at the sort of the Klein bottle model that you have here, you can notice that the hottest regions are sort of the vertical gradients. And that is, of course, consistent with the image of bricks having a lot of vertical directionality. You also have a smidge of horizontal stuff, which is also consistent with horizontality in the image of bricks. So what is the plan that we actually implemented and it worked? We're going to take each one of these images and we're going to think of them as a density function on the Klein bottle. And we're going to do that by, again, looking at its small patches and looking how they distribute on the Klein bottle. What we're going to do next is we're going to do a little bit of Fourier analysis on the Klein bottle. And we're going to represent the density function using Fourier-like coefficients, but on the Klein bottle. And then we're going to try to distinguish images by looking at their Fourier coefficients. That's a sort of an ambitious adventure, but it actually works. So if you don't know what Fourier analysis is all about, let me just give you a one-slide summary. If you have, say, a function from the circle to the complex numbers, and it satisfies that the integral of the function squared magnitude, function magnitude squared is finite, in other words, is in L2 of the circle, then if you compute the following numbers, these are called the Fourier coefficients of the function, these integrals, then you can approximate the function via what is called the Fourier series of the function. It's a sum of sort of sines and cosines, and the coefficients are, again, given by these integrals. So this is what Fourier sort of analysis is, I guess, in principle, is that any function whose integral, whose square integrable can be represented through these coefficients, which are called, again, the Fourier coefficients of the function. So since we're running out of time because of a sort of a small emergency, let me show you what we were able to prove at the end. So I won't be able to show you the why, but I'll show you the what. So here's what we were able to prove. The non-zero elements of this form give you an orthonormal basis for L2 of the Klein bottle. In other words, these will act as sines and cosines for the circle, but now for the Klein bottle. And we will be able to write down sort of density functions in these sort of Klein-led Fourier bases. The second thing we were able to prove is that if you have one of those orthonormal bases, like the one that we just showed you, and you write your probability density function in that basis, then you can estimate the Fourier coefficients from data very explicitly. So here's just a nice formula that you can plug in. You have your data, you have your bases, you get the Fourier coefficients estimated in a nice way. So, so here's the sort of summary of everything that happened. We took a texture image. We took its 3x3 patches, found the corresponding points on the Klein bottle that gives you a density on the Klein bottle, and then represented that density using the Fourier coefficients that you see in the top left. And then using these coefficients, we were able to find sort of very reasonable sort of classification accuracy in sort of interesting databases. So what did we do to sort of summarize everything that has happened? We asked a very simple question. What is the shape of the data of the visual stimuli that humans see? We found that it was a Klein bottle. It's like the nicest model that that was sort of hiding inside the data. Then we use the Klein Bottle as a dictionary to encode texture images. And then we showed that encoding is actually very powerful when you're doing things like texture classification. Going back to the homework for the ones that were getting distracted. This was the images that the computers were seeing, and this was the persistent homology of the space. Does anyone have a guess as to what the space is? For humans, it's a Klein Bottle. For computers, it's a? Yes? No? It's a projective space. That is the kind of homology that we were expecting, that one would expect to see if the data were to accumulate around an RP2. And if you're not convinced that it's an RP2, I've gone ahead and put the actual data set on RP2 for you. And hopefully what you can see is that when you go in the angular direction, that is parameterizing the orientation of the line. And when you're moving in the sort of radial direction, that is parameterizing the displacement of the line. So computers see in projective spaces. Thank you.
Let us thank Dr. Perea for a beautiful talk on a fascinating subject. So, your questions.
Yeah, questions. Let me